Hey everyone. um, we're going to talk about today is a little thing that we like to call Bayes' theorem. And this seemed like a really good place to put it. I mean, usually when people think about Bayes' theorem and stuff like that, it's like, oh, that's advanced stuff. We'll save that to the end after we're done with everything else. But Bayes' theorem isn't terribly complicated. It's just at first it might seem a little counterintuitive. Um, Actually, the theorem itself is intuitive. The results that the theorem gives you is sometimes counterintuitive. But I thought that this would be a good time to bring it up. First of all, let's just hit the ground running. But also we've just talked about the binomial distribution Bernoulli, and so we've thought a little bit about probabilities. So probabilities should be pretty fresh in our minds right now. And Bayes' theorem is simply a way to think carefully about probabilities, and in particular, thinking about what's called conditional probabilities. And those are probabilities, as the name implies, that are conditional. What is the probability of this happening given that this has already happened? And so what I've done then for this is I've created 3 different little vignettes that are all part of this recording right now, which are 3 different ways to try to understand Bayes' theorem. The first one is a Bayesian solution to a brain teaser question called the Monty problem. The second one is trying to solve a story problem that was given to a bunch of people that probably should have known the right answer, but they didn't. Less than 5% of them knew the right answer. And then the third one is more of just kind of a cartoon kind of walkthrough as to why we're getting answers using Bayes' theorem that initially might seem counterintuitive, but maybe if you see it as a cartoon, it'll all make sense as to why we're getting those. And so Bayesian statistics in general is a huge field, and it's becoming increasingly more and more commonly used in fields of biology, especially with kind of genomic type data, but also with really complex ecological data sets when you have lots of potential information and you're trying to come up with, some estimate of what you think that where the world might be given all of this information. And we're going to just briefly just introduce conceptually what the theorem is about. Again, I'm emphasizing that it's based upon conditional probabilities, but a lot of the stuff that we do day in, day out probably apply Bayes' theorem, we just don't even know it. For example, the spam detector on your computer probably is using a Bayesian algorithm to decide whether or not it's just going to take an email and immediately throw it into your spam folder, for example. And it's used in a lot of different fields, and so it's worth having an idea of the underlying philosophy of how it works. And before you start applying Bayesian methods to complex models, first we have to just understand the basics of Bayes' theorem. And that's what the goal is for today, is just to understand the underlying philosophy of Bayes' theorem. Once you complete the work in this course, extending that into a Bayesian framework should probably not be too challenging. And so what we're going to do is we're going to just start off, and I'm going to start off on my first little segment, and we're going to see how it goes. So I'm going to sit back and watch just like you are, and I hope that you enjoy your journey through Bayes' theorem. The first example is loosely based on a game show. And that game show was called Let's Make a Deal. Okay? And this guy right here, he used to host that show in the 1970s. His name was Monty. And there is a somewhat famous kind of brain teaser called the Monty problem. And that's where we're going to start. So first of all, let's go over the game a little bit. the game show basically was just a typical game show where lots of crazy stuff happened, and people were having fun. You'll see that they dressed up often to kind of draw attention to themselves, because generally when you draw attention to yourself, people pay attention. It's like, hey, look at me, I can do this. And then you're like paying attention to me talking about statistics because you're just wondering what I'm doing with that thing on my head. And so that would work pretty well in the game, and people that generally had the craziest outfits would be the ones that were chosen, and there was a whole series of games. But the important bit came with this very last step. At the very end of the game, if you had made it to the final round, you were given the opportunity to open up one of those 3 doors. And behind one of those doors was a shiny brand new car. Behind the other 2 doors was usually something like a goat. I like to think of it as a goat because it usually was a goat. But sometimes it was a donkey, sometimes it was chickens. Doesn't really matter. It was just something that you didn't want, or at least you certainly didn't want as much as you wanted that brand new shiny car. And so going in, and this was always fun for the audience because they'd be screaming, pick door 2, pick door 1, pick door 3, and stuff like that. But it really didn't matter at that point. You had no idea what was behind A, B, or C. And here's the possible combinations. A could have had a car, and B and C have a goat. B could have a car, and A and C could have a goat. And C could have a car, and A and B could have the goat. Notice that I'm picking an appropriate yeared car because I don't want to be accused of any kind of an anachronism. But the point is that we don't know what to choose, right? They all have an equal possibility of having that car, but eventually the contestant would pick one. So let's say, hypothetically, let's pretend that you're the contestant, and you decide to choose A. And so you would choose A, and then Monty would go over to either of the other 2 doors and open it. He would never open your door. Absolutely under no situation would he ever open your door. And he would open a door, and that door would always have a goat behind it. And again, you don't want the goat. So Monty will always choose a goat. He will never choose your door. So at this point in the game, everyone's like, whew, well, thank goodness there wasn't a car there, because then the game would be over. But again, Monty will never open up a door that has a car behind it. And so then what Monty would do is he would ask, would you like to switch doors? Right? You originally chose door A. He showed you that there is a goat behind door B. And now he's asking you once again, do you want to change your mind? Would you rather choose C, or do you want to stick with A? And of course then the crowd would go nuts, and they would be yelling, switch, don't switch, stay, stay. Or they would be yelling, it doesn't matter. They would be yelling all of those things. And so this was the challenging thing, like, do you switch doors? Well, it turns out that you should switch doors. On average, if you switch doors, you're going to win a car 66.6% of the time. So it's not guaranteed you're going to win, obviously. But you have a much higher probability of winning that shiny new car if indeed you switched curtains. And so this puzzle was originally made somewhat famous in a magazine called Parade Magazine. I don't know if Parade Magazine still exists, but back when people would get print media, Parade Magazine would come with everybody's Sunday paper. And there was a section in that paper called Ask Marilyn. And at that time, Marilyn was supposedly the smartest person in the world. She had the highest IQ ever measured in anyone. So she had this column where people would ask her like brain teaser math problems they maybe are confused about, and she would answer them. And somebody asked her this question about the let's make a deal situation. Like, do I switch doors? Do I not switch doors? Or it doesn't matter? And Marilyn said, yeah, you switch doors. If you switch doors, you're going to win 66% of the time. And at that point, everyone seemed to go crazy, and she received thousands of letters of hate mail, including hundreds of letters from people that had PhDs in mathematics and statistics, including the head of statistics department at very prestigious Ivy League schools, basically saying, you know, maybe you shouldn't do math because you're not as smart as everyone thinks you are. But the joke was on them because she was actually correct. And she finally convinced people, even though it took some people years to be convinced, she actually convinced people that she was correct. But this is why it's a brain teaser, because it really is, it's not intuitively obvious why it should matter at all to switch doors. And so let's think about it when we went in. When we went in and we were given our choice to switch a door, each door had a 1/3 chance of having the car, and likewise, each door then had a 2/3 chance of having a goat. And again, if we sum up these probabilities for any door, they're always going to sum to 1. Probabilities always, always, always sum to 1. And so when Monty chose a door, he will never pick the door with the car. He will always pick a door with a goat, which means that he's actually provided us information. Now we know that the probability that the car is behind door B has to be 0 out of 3. And we have these 2 doors that are remaining. And so we can think about what's the likelihood of them having a car or having a goat. So we know that curtain B has a 0 out of 3 chance of having the car and a 3 out of 3 chance of having a goat, because he's already showed us the goat. Now we can think about what is the probability that A or C has the car or the goat. And so now it's 1/2. And this is where people get hung up with this brain teaser, is because it still seems like it doesn't matter. You should be able to pick A or C, and you should have the exact same probability of successfully getting this really, really nice 1978 Chevette, which probably had, I don't know, it must have had at least 0.8 liter engine in it. So that's where people stop. But what they forget is that Monty actually gave us information. Here, I'm going to move myself down because I'm emoting with my hands and nobody can see how excited I am about this. He's actually given us information. He didn't randomly pick a door. He knew exactly what he was picking. He was going to pick a door that we did not choose, and he was going to pick a door that did not have the car behind it. Okay? And so let's rethink about going into this whole thing. Our prior beliefs were that each door has a 1/3 chance of having a car behind it. Now, once Monty picks door B, we can think about, well, what is the likelihood that door A has a car behind it? And so now that's changed. Okay, our probability has changed because we've gotten new information. And again, this will always have to be 0 out of 3 because Monty will never show us a car. He would never, ever do that because that wouldn't make the game fun. It would go too fast, not as much advertising money, there's lots of reasons. Okay? And so let's start with thinking about what our prior probabilities were, our prior beliefs. Our prior probability was that each door had a 1/3 chance of having the car behind it. And since we chose door A, let's focus on that. Let's think about what is the probability that A has a car behind it, and that's 1/3. Next, after Monty chooses door B and shows us the goat, now we can think about the likelihood. But let's think about what is the likelihood that Monty would choose door B if indeed we had chosen correctly. And if we had chosen correctly, the way that we would say this formally is, what is the probability that Monty would open door B given that the car is actually behind door A? And that's going to be 1/2. And it's going to be 1/2 because if it actually was behind door A, Monty could have chosen either B or C. And so what we want to think about then is, well, what is the probability that he would open door B over all possible places where the car might be? Okay, and we can think about this as being the probability of the data. And here the data is the fact that Monty opened door B. And so we have three different things here that we're going to be interested in. We have the prior probability that it was behind A, because again, we had no information. Once we know for sure that it's not behind door B, well, now we have the likelihood that he would open door B given that it's actually behind A. And now we want to just think about the probability of the data. What is the probability that he would open door B? And we can run through the different ways that he might have done that. So the first way he might have done that is we can think about what is the probability that he would open door B if indeed the car were behind door A. And we're going to take that, which is 1/2. We've already figured that out because we got the new information, and if he chose door B, we know that there's a 50% chance that it's here and a 50% chance that it's behind C. And we're going to multiply that by the probability that A even has the car. So that's going to be 1/2 times 1/3 equals 1/6. So that would be the probability that we expect that he would open door B given that the car is behind door A. Next, we can think about what is the probability that he would open door B if the car actually was behind door B, times our probability that the car is behind door B. Well, right here, this conditional probability, what is the probability that he would open that door if the car was behind that door? We already know the rules of the game. He would never do that. So it's 0 out of 2. He would never ever do that. Times 1/3, again, our prior probability that the car is actually behind door B. And so it's going to be 0. There's no way that he would ever open that up. Next, we can think about, well, what's the probability he would open door B if the car was actually behind door C? Well, he's never going to open up your door, and he's never going to show you the car. So the probability that he would open up door B if it actually were behind door C has to be 1. He's got no choice. But then again, we'll also multiply that by the probability that the car actually is behind door C in the first place, which again is 1/3. So that's going to equal 1/3. And so the probability that we would expect to see him open door B, given all of these different possibilities then, the probability of our data, which is and again our data is he opened door B, is going to be 1/6 plus 0 plus 1/3, just summing up these numbers, and that's going to be 1/2. And so what we can do then is we can calculate, because this is the thing we're interested in. This is the money right here, right here. Actually, it's not the money, it's the car. But they probably allowed you to sell the car or take cash value, but I digress. We want to know what's the probability that the car is actually behind door A given that he opened door B. We can think about this as what's called the posterior probability. In the posterior probability, how we're going to calculate this is we're going to take the probability that he opened door B given the fact that the car is behind door A, and that's going to be our likelihood, times our prior probability of having a car behind A. So this is when we had no information. This is after we have some information, because we have data here. We don't have data here. All we have is a probability. And then we're going to divide it by the probability of our data, all the different ways in which that he would open door B. So this is what Bayes' theorem is. This is Bayes' theorem. Posterior probability equals the likelihood times the prior divided by the probability of the data. Or in a formal way, we can do it as probability of A given B and probability of B given A times the probability of A divided by the probability of B. And so going back and thinking about our problem again, we chose curtain A, or door A, and Monty showed us a goat behind door B, and now we've calculated these probabilities, we can put them into Bayes' theorem. And so the probability that the car is behind curtain A, given that he opened B, is going to be the likelihood, which is 1/2, because again, he's already opened door B, so we're going to say there's a 50-50 chance that it could be in either of these, multiplied by our prior expectation, which is a 1/3 chance for all three of those, divided by the probability of the data. And again, here, the probability of the data is simply the probability that we expect to see him open door B, given that we've chosen door A. Okay, so that's the probability of our data. And so if we want to think about this as a posterior probability, the probability that the car is behind door A, given that he opened door B, is 1/3. So 0.33 is our probability, which means that the probability that it's behind door C, given that he opened door B, must be 1 minus 1/3, which is 2/3. And so 2/3 of the time, you're going to win that car, and that's really what the goal always is. And so that is the Bayesian explanation as to why the Monty Hall problem is not only a brain teaser, but why Marilyn Vos Savant was correct in Parade when she said, you always want to switch curtains. Now, this wouldn't work if Monty had randomly chosen one of these. It wouldn't work, meaning that there would be a 1/3 chance that he might open your curtain, or there's a 1/3 chance that he might expose the car. Monty followed very specific rules. He would never open up your curtain, and he would never show you the car when he opened up a curtain. And as long as we understand the rules of the game, we can adjust our expectations accordingly. And if we adjust our expectations accordingly, we should feel pretty confident that 2/3 of the time, the car is probably behind one of those, or behind the other curtain, not behind the curtain that we chose. And so that is the end of example 1 of getting our heads around conditional probabilities and Bayes' theorem. Okay, let's try example 2 to thinking about getting our heads around Bayes' theorem and conditional probabilities and how we can actually use them to give us kind of an informed idea about a particular event happening. And the example that I want to go through here is often called the classic example. And so I figured it would be a good idea to use the classic example. And it's the classic example because it was famously used by a psychologist who was doing research about how humans perceive probabilities, or how we think we can do probabilities in our head, and it might not necessarily be accurate. And so the origin of this problem was in the 70s. I believe it was in the early 70s. Researchers went to scientific meetings for oncologists, so physicians that specifically studied cancer. And they went to a couple of different conferences, I think in Europe, Germany, and maybe England, and then also in the US. And clearly these are people that are going to these conferences. They should be at the top of the field, and clearly, hopefully, they're pretty bright people. And the question posed to the audience as kind of a story problem was as such. So let's assume that the probability of breast cancer is 1% for women at the age of 40. So we're gonna assume that that's just the baseline. So we would expect maybe 1 out of every 100 individuals to have cancer. if a woman has breast cancer, the probability is 0.8 or 80% that she will get a positive test, okay, that it will show up positive. If a woman does not have breast cancer, the probability is 9.6% that she will also get a positive test. In other words, we can think of this as this is a false positive rate. Okay? So the question given to all of these very smart doctors was, let's say that you were to randomly select somebody from that was 40 years old and they got a positive test. The question is, what is the probability that that person would actually have cancer? And less than 5% of these very smart people were even remotely close to the right answer. And so it's a tricky question. And so what I think would be helpful maybe for you is to, hit pause and see if you can answer this. Normally, if we were in a classroom, I would take 5 minutes and let people work in groups and let them see if they could figure it out. So I encourage you to hit pause and see if you can figure this out on the fly, and then we'll come back and we'll take apart what we know, and we will apply Bayes' theorem, and we will arrive at the probability that this individual, this randomly selected individual of the age of 40, actually has cancer. Okay, so what we start with is, what do we know? We know that 1% have cancer, okay? Of this population, we know that. We know that 80% of tests detect it when it's present, right? So when it's present, that test is going to be accurate 80% of the time. We also know that 9.6% of the time, we are going to have a false positive. But we can think about, let's say, positive test, but no cancer. Okay? And so this is when this 80% accuracy, it'll detect it 80% of the time when it's actually present, but it will also detect it 9.6% of the time when it's not present. So this is the information that we have. And from this, we should be able to predict the probability that that individual actually has cancer. And so one way of formally setting this up is we're interested in what is the probability of cancer given a positive test. Okay, that's what we're going to try to solve for. And this is going to be our posterior probability, right? Because our data is the positive test. That is our data. And so we want to know what is the probability of having cancer, or we could think about this as the probability of the model. We could think about this as the probability of the hypothesis. Maybe that's the clearer way to think about it in this framework. So there's a hypothesis that the person is indeed has cancer, and what we want to know is what is the probability of that hypothesis being true given that we have a positive test. And the way that I like to approach these problems, and it makes it easier, is to make a table. And so we can think about what are the possible outcomes for the test. You can either test positive or you can test negative. And then what are the possible things that could result in this test? Well, you have cancer or you don't have cancer. And we already know this information from the general population. Probability of having cancer should be 1%, and the probability of no cancer then should be 99%. And so now we can go through all the different ways that we might get this. So let's start with if the patient has cancer. You expect to get a positive test 80% of the time. The probability, given that you have cancer, conditional probability, if you have cancer, the likelihood that you're going to get a positive test is 0.8, which means that the likelihood you're going to get a negative test is 0.2. Okay. Likewise, you can have a positive test but not have cancer. We know that that's going to happen 9.6% of the time. So that's going to be 0.096. And then if you don't have cancer, negative test, we would expect that 0.904 with that probability. 90.4% of the time, we would expect to have a negative test. So again, our probabilities are adding up. 0.8 plus 0.2 is going to equal 1. So if the patient has cancer, you're either going to have a positive test or a negative test. Those probabilities will add to 1. And if the patient does not have cancer, there's going to be a probability of a positive test, probability of a negative test. You add those two together, and they're always going to equal 1. And so we can think about this 0.8, because this is what we're interested in, the probability of cancer given a positive test. And so if you have cancer, positive test, the probability it's going to be detected is 0.8. We can think about that as our likelihood. And our prior probability of that patient having cancer is 1%, or 0.01. So I'm going to scoot back to R here because I think it's easier for me, at least it is, than turning around in circles, because we can make R look all pretty like this. We can do that. We have that power. And let's see here. I'm going to bring my R down. Oh, there, R's already down there. Well, good for us. So I'm going to recreate that table I had on the whiteboard. Okay, so that's exactly what I wrote on the whiteboard. I will put myself in the lower right-hand corner in case I get really excited and I want to emote. And so this is what we had on the board again. And let's just go ahead and just do this. Let's create an object called likelihood, because we know what the likelihood is of the patient having cancer, or we know what the probability is of having a positive test result given that the patient has cancer. And so that's going to equal 0.8, but we'll just be explicit so that way it can be flexible. And we're going to say first row, first column. Indeed, it's 0.8. Next, we can think about the prior. And the prior, as we said, is 0.01, because we expect 1% of the population to actually have cancer. And next, we have to think about all the different ways in which we could get a positive test. And this is going to be our probability of the data. And so what are the different ways in which we could get a positive test? Well, we can take the likelihood, spell likelihood, which again is right there. It's the 0.8, right? Likelihood is 0.8. And multiply that by the prior probability. Okay, so that's what the expectation is for getting a positive test. And then we'll add to that the probability of getting a positive test if you don't have cancer. Okay, so that's the probability of getting a positive test. If you do, this is the probability of getting a positive test if you don't. And we'll take that and we're going to multiply that by what? Well, what's our prior belief for that scenario? If we expect 1 out of 100 or 1% to actually have it, that means we would expect 99% or 0.99 to not have it. And so we'll go ahead and we'll write it up being really nice and explicit, 1 minus 0.01. And so these are all the different ways that we can have a positive test. I didn't run that. Likelihood, did I spell that wrong? Likelihood is that, prior is, oh, there's the problem. Didn't put that object in there. Okay, and so that is the probability then of our data. And then we can go ahead and we can pop that into Bayes' theorem. So our posterior is going to be what? It's going to be the likelihood times the prior divided by the probability of our data. And I got to spell things right. That often helps. Just run all this stuff again. So again, here's our matrix of our information. This is the likelihood that if you have cancer that the test is going to detect it. This is the prior probability that any random individual has it. That's the probability of the data. That's the probability associated with having a positive test. And so we can go ahead and we can ask what the posterior is. And the posterior is 0.077, or we can think of that as 7.8%. And so that's really pretty low, right? And you can imagine why this is considered the classic example, because clearly Bayesian statistics is somewhat counterintuitive at first, because humans don't necessarily always think about probabilities in the correct way. And the fact that this story problem was given to people that undoubtedly are incredibly intelligent people means that even the most intelligent people among us can have difficulty thinking about how to think about conditional probabilities. And so that's a pretty low number. And obviously that is the kind of number that would be pretty nice to have if you were a physician and a patient came back with a positive test. Instead of thinking the test is 80% accurate, which is what many people would assume. It's like, well, there's an 80% chance you have it if the test is 80%. But there's only a 1% chance you have it overall when you walk into the office. And so actually, the probability that you have something to be very concerned about isn't 80%, it's less than 8%. And that would be really good information to maybe communicate to a patient before, because maybe it's going to be 4 more days before we can do a follow-up, and then people are going to lose sleep for 4 days because they think that it's 80% chance, when in fact it's less than a 10% chance. And so this is why it's important to always consider what the conditional probability is. And once you have more information, we could frame it as, what is the probability that would be positive, taking into account a true positive is very rare. I mean, a way to think about it is we have this true positive rate here, and then we have this false positive rate. Well, the false positive rate is really small compared to the true positive rate, but there's only 1 out of 100 people that have it. Whereas that means there are 99 people, and once you start sampling 99 people, even though that's a low false positive rate, you're going to end up with a lot more false positives than you end up with true positives, even though the true positive rate is higher than the false positive rate. And so this is something to think about and play around with. Okay, part 3 of trying to see how good we feel about thinking about conditional probabilities and thinking about Bayes' theorem. And this is going to be more of a cartoon example. It's just going to be a visual story problem, much more than it is about, hard number type things. But hopefully, if there are still parts of this that you're like, I don't quite get it, hopefully this will help out. So this is a different way to kind of explain the same thing. And I'm going to start with a hypothetical example that will actually be similar to the last example. And I'm going to assume that there's some disease out there where the probability of infection is equal to 0.1. So we would expect 10% of the population to be infected. We have a test, and let's say that the true positive rate for that test is 0.8. So we expect that we will be able to detect that particular infection 80% of the time when it's actually present. Likewise, we have a false positive rate, and we expect that 20% of the time we are going to get a positive test when the infection is actually not present in that individual. So I'm saying let's pretend that we have a population size of 100 individuals to make the math really easy. And all of those dots down there represent individuals in a population of 100. And I've marked 10 of them as orange, and those are our infected individuals. So that is the 10% of the population that we expect to be infected. And here's the 90% of the population then that we expect to not be infected. So we go ahead and we do our positive test, or we do our testing on it, and we expect to detect it when it's present 80% of the time. And so there's our 80% true positives. Since there were 10 in the population that truly were infected, we expect to detect 8 of them. And likewise, we have our false positives. We expect 22% or 20% of the healthy individuals in the population to come up as a false positive. So they would get a positive test result. And so that would total out to, we would expect 18 individuals out of 100 to have a positive test, even though they're not infected. And we would expect 8 out of those 100 individuals to have a positive test because they actually are infected in the population. And so once we have those numbers, we know how many total positive tests there are in our sample. It's going to be 18 plus 8. And we want to know what is the probability that an individual is truly infected given that they have a positive test. And so we can write that out as the probability of being infected given you have a positive test as being simply 8 over 8 plus 18, and that's going to roughly equal 30.8%. And so that really is the nuts and bolts of what Bayes' theorem was telling us. And we could convince ourselves of that by staring at these dots a little bit longer and thinking about how did we calculate this? And basically we took this red rectangle here, and that was that was the number of individuals that we would expect to see given a probability of being able to detect it at 0.8 times the probability that they actually were infected. And we expect that to be 10% of the population. So that was 8. And down here in the denominator, it's all the different scenarios in which we might get a positive test. And so again, we would expect 8 individuals to be positive because 8 out of 10 is what we expect to see. And then we have here the other individuals that we expect to test positive, and those are our false positives, and that ends up being 18 out of the remaining 90 individuals in our sample. So we can think about, again, thinking about this being, this is our little red area here, that's where we have a true positive, and this blue area here is where we have a false positive. So overall, we expect this is what the actual population looks like. We should have 10 out of 100 that are infected, and we should have 90 out of 100 that are not infected. And then we go ahead and we run our test on it. And what do we have? Well, we have the probability of a positive test given that you're infected. We expect 80% of them. There's our 8 individuals that are in red. and we expect a positive test if you're not infected to occur 20% of the time, so 20% of 90, do some arithmetic, and it's 18 individuals. And again, so we know why we know why we have 8 individuals here, because we have the expected number of infected individuals, and then we have the probability of detecting an infected individual, and that's going to be 8 out of 100. So that's our true positives. And likewise, we will also have our false positives, and we'll calculate that the same way. We expect 90 out of 100 to not be infected. We expect to get a false positive 20% of the time, which means that we expect 18 out of 100 individuals to, out of the whole population, to be infected. And so again, that's where we get the infected given a positive test. And if we look down here again in the numerator, that is the probability of the data. And that's because there's 2 ways to get a positive test. You can either have a positive test because you do have an infection, or you can have a positive test even though you don't have the infection. And so that's going to equal 0.26. And then up here in the numerator, or I'm sorry, in the denominator, we have the probability of a true positive. And that probability of a true positive, that probability of a true positive is the probability, or the prior probability of how many individuals we expect to be infected times the probability that we'll detect those individuals. And so that's what we have here in the denominator. That's that ratio that we put together. And since that's how we calculated that, that is Bayes' theorem. That was just kind of a cartoon kind of view of how Bayes' theorem works. We have the probability of a positive test given that you're infected times the probability that you actually are infected, divided by the overall probability of having a positive test. And so we can think about this again as the probability of the model given the data. Here the model is, we're interested in the infection, so what's the probability of infection given the data? But now we can be more kind of maybe perhaps pedantic about it and say the probability of the model given the data is going to equal the probability of the data given the model times the probability of the model divided by the probability of the data. We can think about the same thing if we want to frame it as a hypothesis. The hypothesis is that the individual is infected, and we want to know what supporting evidence do we have that an individual is truly infected given they have a positive test. So we could say, what is the probability of the hypothesis given the evidence? That's going to be our posterior probability. Is going to equal what? It's going to equal the likelihood, which is the probability of the evidence given the hypothesis, times the probability of our hypothesis, divided by the overall probability of the evidence. Or we could just simply say our posterior probability is equal to the likelihood times our prior probability divided by the overall probability of our data. And when we go ahead and we do that number crunching, 0.8 times 0.1 divided by 0.26 equals 0.38. And that is the same number that we got when we did it in the brute force way, which was somewhere back here in one of these. Where was that? Oh, there it is. Which was right here, right? When we did it in the brute force way, we got 30.8. When we applied Bayes' theorem, we get 30.8. And so that's just kind of a graphical demonstration of what we've been trying to do with understanding Bayes' theorem and the utility of understanding conditional probabilities. And as I said in the beginning, Bayes' theorem is used widely in a lot of different fields of not only of science, but also, that's how, your spam detector works on your computer is actually to use Bayes' theorem. And so it's always useful, I think, to understand conditional probabilities. And understanding conditional probabilities will become actually important in the future when we talk about the pros and cons of interpreting p-values, for example. We can make a Bayesian argument as to how we should really be thinking about p-values. And those are another thing that people often misinterpret. So, okay, well, I hope that you enjoyed this little introduction to Bayesian approaches, or Bayes theorem, Bayesian statistics, if you will, very basic Bayesian statistics. But yeah, so that gives you something to cogitate on. And I know that it's pretty weird at first to kind of get your head around exactly what it's trying to do, but I think once you get it, you're always going to be asking what the conditional probability is for any particular event to occur. So good luck playing around with this stuff. If you kind of enjoyed it, or if you need to have a little bit more maybe motivation, or maybe you like to read science books, I don't know. But there's actually a really good book, and I do not know the publisher and I do not know the author, so I am in no way, shape, or form getting any kickback, and plus you can get this used almost anywhere on the Amazons. But it's called The Theory That Would Not Die, and it's a pretty cool book. It talks about how they used Bayes' rule to break the Enigma code, which was a really big deal. It kind of resulted in the end of, or at least a large part of the change in the direction of the war, of World War II. How it was used to hunt down Russian submarines, so that's exciting. And then they talk about the 2 centuries of controversy. And most of the controversy that's surrounding Bayesian statistics is that for a lot of practical problems, it's really rather easy to come up with a prior, maybe. But it gets tricky because people will disagree on what the prior probability should be. The likelihood is usually easy to come across because that's usually based upon some data that you already have, and then you've chosen to model it in some way. The sticky wicket, if you will, for Bayesian statistics for a lot of applications historically has been the denominator, that it's very difficult and sometimes not possible to calculate the probability of the data. But now that we have really fast computers, that's not as big of a problem anymore because we use other methods of exploring the surface of the posterior distribution. And some of us will revisit that. All of us are welcome to revisit that, but the people in the 560 section, we will revisit that to understand how we can basically ignore the denominator of Bayes' theorem. And spoiler alert, it's using Markov chain Monte Carlo to explore the parameter space. So at that, enjoy the world of Bayes.